So let's look at how you actually do this in R, because of course we're not gonna, I mean, you can if you're really crazy about it. You can try to implement this for yourself and write a little for loop where it iterates and goes downhill and whatnot. But R will just do it for you. So let's have a look at how that's done. Let's look at a particular, we'll do this in the context of a particular data set. So you can download that data here. Let's get rid of all this. So this is the URL. You can copy it from this video. If you like, just pause the video and copy it. I made it small. So it's just this little string is all you need to copy. Or like I said, remember it's in the slides. These links should work too. But you can copy it from slide 45 here. And this is what we're going to use to play around with. So this is a little function that just prints out some summaries about the data frame so we can see it. So this is a data frame with a little over 1,000 rows, and there are 7 columns. And the columns are age, sex, BMI, children, smoker, region, and charges. So each row represents a person, and we have recorded their age and their sex. BMI is body mass index. Children is how many children they have. Smoker is exactly what you would think, whether they smoke or not. Region is which part of the country they're in. So I think there's 4 regions here: Southwest, Southeast, and Northwest and Northeast. And then charges represents how I believe how much they build for medical insurance in a given year. In the given year. So this is data for each person for a particular year. So what we're interested in here is predicting what somebody's insurance cost is going to be in a year based on what we know about them. Okay, so the way that we do that, let's fit our linear regression model. In R, the most generic command to do this is lm. So you can look at, if you want, a little bit about lm here. So fitting linear models. So the basic syntax is you have lm, and then you type the whatever you want the outcome variable to be. So in this case, I want charges to be the thing that we're predicting, and then you put a little tilde, and then you put what you want to use as your predictor. So here, I'm just going to start with using a single predictor, age, and then you say what are the data that you're going to use. So here I'm going to use the insurance data. All right. So this thing here is called in R, it's called a formula. It's just like a little bit of syntax that is trying to abbreviate what the functional form is supposed to look like. So, for example, what we're really saying here is that I want charge to be some, like approximately, right, equal to some slope times age plus an intercept, right? This is really what we're saying. And so here, this is like our little shorthand for that. So maybe actually here, approximately. Saying approximate this variable with some constant times age plus some intercept. So the intercept is implicit here. I mean, I think you can write explicitly like that, but it assumes that you want an intercept if you don't put it there. So that's it. Charges, sorry. Okay, great. So if I do that and I just press enter, it runs. And what you can see here is it returns some object, and it tells you what the coefficients are. So the coefficients are exactly these, like the slope and the intercept that's what that means. So the slope for age is 257, and the intercept of this that it found is 3,165.9. So this is our like fit prediction function now. And if you want to get, so I can assign that into something. So let's just call it m. If I want to get the coefficients out, I can do it like this. So that returns a vector. So I can do like this. So that will give me the second thing, and this is the first thing. So this gives me just like a vector of of the coefficients. If I want to get predictions, I can use the predict function. So to use the predict function, I pass it first the model that I fit, this model object, I guess you could call it, and then you put in the data that you want to predict on. So in this case, I just want to get the predictions for the same data. And you can see that this is my, so for example, these are the predictions for like the second person in this data set. So if I want to, for example, do like a mutate, do something like this. Okay. So here I have the actual charges, and then these are the predicted charges according to our regression model. And you can see that they're not perfect here, right? And if I want to look at, for example, what's the mean squared error of this prediction, I can do something like this, right? That is the mean squared error. I can also take the square root of the mean squared error. This is what we call the root mean squared error. Or RMSE. RMSE, MSE, basically the same thing, right? It's just taking a square root or not. The reason you take the square root is so that it's this is interpretable as like an amount of dollars. So this is like the average prediction error. Usually what I'm saying here is that the usual amount that I'm off by in my predictions is $11,000. Whereas with the mean squared error, it's just that thing squared. So this is like 13, I don't know, what is this, like 133 million square dollars, I guess. It's more interpretable usually if you look at the square root of the mean squared error. But in terms of doing the optimization, they're the same, because if one's just the square root of the other, if you minimize mean squared error, you minimize root mean squared error. So they're like basically interchangeable in terms of the optimization. So people prefer to work with mean squared error with the optimization, because why take an extra square root? Whereas if you're interpreting these things and looking at output, usually the square root of that is a bit more interpretable. It's kind of like the difference between like variance and standard error. Really, they're basically the same thing. They're telling you the same thing, but the standard error is more interpretable as like an actual distance in the units of a random variable, whereas the variance is just more mathematically tractable to work with sometimes. Right, so that's the mean squared error. That's how you get predictions. So we've seen a little bit about the formula interface. We've seen how to get the coefficients out. We've seen how to make predictions with that object. Now we're going to look at using multiple predictors. So when I was explaining linear regression, I was only talking about in terms of one predictor, but you can do linear regression with multiple predictors as well. So for example, let's say I want to use age and BMI as predictors. I can do that perfectly easily in the formula interface. I just have to do a plus BMI here. And what that means is that I'm doing the function that I'm fitting looks like this. So I'm saying let charges be approximated by some intercept plus some slope times age plus another slope, I don't know, let's call that R, times BMI. So now there are three parameters. There's the intercept, there's what we call the coefficient on age, and there's the coefficient on BMI. But I can fit this the same way, just using gradient descent by trying to find the values of B, M, and R that give me the lowest loss. And again, I don't have to do it. R will do it for me. But conceptually, that's all that's happening, is that it's fiddling with these three knobs until it gets the values that give the lowest mean squared error. And that's what happens when I press play here. And so if I look at M, now you can see that those are the three things that it gives me back. It gives me back the intercept, it gives me back the coefficient on age, and the coefficient on BMI. And you can see that this is different than it was before. So when I just had, well, let me just rerun that like this. Okay, so if I just include age, the coefficient I get is 257. But if I add BMI, and the intercept is like 3,000, right? But if I add BMI, my intercept becomes negative 6,000, and my age coefficient goes down to 249. And now this thing goes up to 333. If you think about it, what's going on is like here, I don't have a BMI value, so it's like setting this to 0, right? And if I force this to be 0, well then like the whatever effect that BMI is having on charges that I could explain with some coefficient, it needs to be absorbed somehow into any of that that is like predictive or somehow helpful is getting absorbed into these numbers, into the M or the B, or not being used. And so it absolutely makes sense that these numbers can and should change, right? Like all I'm doing, there's no kind of like causal interpretation here, right? It's just finding B and M that give the lowest loss. And if I force this thing R to be 0, right, then the numbers M and B that minimize the mean squared error are going to be different than if I say actually let R be something else and find the minimum, right? These numbers don't actually have any inherent meaning. They're just coefficients. They're just things that we're multiplying other things by to try to get the something with the lowest mean squared error. And so yeah, absolutely. If you add a variable to the regression model, these other things can move around and change, and you should expect that. And generally speaking, don't interpret them, although that's what people do. Okay, so this is how you add a variable to a prediction model. There's also, okay, so also I want to show you what happens if you have categorical predictors. So here age and BMI are both continuous values, like age, between like 0 and 100, BMI is, continuous values between like 25 and 35 or so. But in this data set, there are also these predictors which are like region, right? It has like 4 categories, or a smoker has 2 categories. So what happens if I put in, for example, region here, right? Like how do I multiply, I don't know, let's call this other coefficient C times region, right? Like this isn't a number. So how do I do that? That doesn't really make any sense. So what's going to happen here is that, I'll show you, if I add in region, it actually automatically breaks up region into different variables that indicate whether, so here we have made a new variable called region northwest. Region northwest is 0 if region is not equal to northwest, and it's 1 when region is equal to northwest. Whereas region southeast is the same thing, but for southeast. It's an indicator of region equals southeast. This is an indicator of region equals northwest. This is the indicator of region equals southwest. And then you may be wondering, well, where is the indicator of region equals, which is the one that we're missing, northeast, right? And it actually doesn't need to have that one because that kind of is like the intercept. If it had that one, it would actually, I guess I don't want to get into that, but it wouldn't be able to fit the model uniquely. So it's kind of like the base case. In the base case, where it just defaults to what the value of the intercept is. I realize that's a little hand wavy, but these are called dummy variables, and it's like a common way of dealing with categorical data. And you can do it explicitly too. So if you want to actually control and see how things are working, I recommend looking into the function model. I think it's called model matrix. Yeah, okay. So if I do model matrix, I can do, so for model matrix, you just do like the right-hand side of the equation. So I'm just gonna do like this. And let me just show you like age plus BMI on insurance data, just to give you an example. So this is straightforward. So it does, it creates all of the predictors that it's going to need in the linear regression model. So it creates the intercept. So here, because you can actually think of, so B, the intercept, it's the way that in R it conceptualizes it is B times 1. So you have this other predictor that just takes the value 1 across the entire data frame. And then B, the intercept, is actually just a coefficient. There's nothing special about the intercept. It's just a coefficient on another predictor. Just so happens that predictor is always 1. Okay. So it creates this intercept column, and then it creates an age column and a BMI column. And since these things are continuous predictors, it doesn't do anything to them. It just puts in the intercept. But now we can see what happens if I do, let's look at just region. Okay. So now it makes these dummies, right? So it has the intercept, and then it has all of these so-called dummy variables. So if I were to look at the first row of my original insurance data, we would see that the region would be southwest. And for the second person, their region is southeast, and the third person is southeast, and the fourth person is northwest. And then let's find somebody, okay, this person, for example, these ones are all zeros, and we have the one in the intercept. So that person is northeast, okay? So this is kind of under the hood how R is creating the matrix of predictors when there are some categorical variables. So you can control it explicitly if you use this kind of model matrix thing. And you can also use, instead of using the LM thing here, right, if you want to explicitly create this matrix yourself, which is sometimes useful, like if you want to, for example, tightly control how you're like filling in NAs and things like that. I'll show you how to do that in a sec. So you can use, I like this package, tidy models. And in tidy models, we can explicitly control what the predictor matrix and outcomes are. So here I'm just going to say let Y be the insurance, the charges column. So we can look at Y, right? Okay, so that's the thing I'm trying to predict. And then I'm going to create the matrix of predictors. So insurance, and I'm going to take, for instance, let's say I want to use this children. I want to use the children column, but instead of making it be a numeric, like 0, 1, 2, 3, that would force it to be to find a linear relationship between charges and children. Like effectively, it forces it to mean that more children are more charges or more children are less charges. But maybe the relationship is actually for 1 or 2 children, it's more charges, but then for 3, it's fewer. Somehow there's an economy of scale for children. I don't know. So either 0 and 3 is lower. So I actually want to treat children as a category rather than as a numeric. So for example, I might use a mutate and say children is equal to factor children. Okay. And then let's say I want to take out charges, and then everything else that's left over, I want to create this model matrix. The way that I indicate everything else that's left over is with the dot. So this is the formula. The other thing is that I want to pipe all of this into actually the second argument in model matrix. So the way I do that is with, unfortunately, so here the dot actually means something different than it does here. Here this dot means pipe all this stuff into the second argument. Here this dot is part of this first argument, this special formula syntax, where it means everything. So I'll show you what I mean. So if I just type X, I get this whole, I need to select everything except for charges. And now I print that. Okay, there we go. So we can see we get a whole bunch of little, okay, so here are the variables that we have. We have intercept, we have age, we have sex, which it also made a dummy, but here the dummy is kind of equal to the thing in the beginning because it was already treated as binary. And then I have children 1, so this is indicating that this person has 1 child. children 2 indicating, this person has 2 children, children 3 indicating, for example, this person has 3 children. And so it has created these different variables. And now I have like my column, which is my predictors, and then X, which is a matrix, my thing I'm trying to predict. And then X is my matrix of predictors. And I can put that in. Now I use tidy models stuff. So linear reg just says set up a linear regression. Don't do anything else. Just kind of set it up. And then if I want to fit it, I can use fit XY. And then I can explicitly pass this matrix and that output. And let's save that into M. M. And I can print this, and then you can see that this is actually like under the hood. It's doing the same thing. It's just getting all these coefficients, but you've just done it more explicitly controlling the inputs and whatnot. So then similarly, if I wanted to predict there, I could do like M and then predict for this whole matrix X, and then these are all the predictions that I get out. And the output here is slightly different. Also, it gives it to you for tidy models. It gives it to you as a data frame with a single column. So tidy models is just like a nice package, because if you learn how to use it, you can actually you can use other things besides linear regression. You can do all sorts of cool machine learning stuff, really using the same kind of code as you do for linear regression. So it lets you generalize to these more advanced techniques without much effort. So I think it's kind of worthwhile to play around with it a little bit. And by the way, here you can also, if you wanted to, with tidy models, you can also use this like standard formula interface. So I could do fit charges, regress that onto like age plus BMI plus, well, actually here, let me show you something else. This little dot syntax here, I can use that in the formula syntax as well to just say everything else that's in the data frame except for charges, I want to treat those, everything else as predictors. So, because otherwise I would have to type age plus BMI plus smoker, blah, 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 right? And if I just want to say put everything else in there as on the right-hand side, I just use the dot for that. And data equals insurance. And this gives you the same thing. Okay. So here you can see the difference is that since I didn't do this kind of explicit control of things, it just treated children as a continuous variable, right? So there's only one coefficient here. It didn't break it up into dummies the way it did for region, because region is it did that automatically because it's a character. So it doesn't know how to turn that into a number. And instead it just makes dummies, which makes sense. But you want to always look at your data and understand what's being turned into a dummy variable and what's being treated as continuous, and make sure that you're doing that in a way that's intentional and not just relying on the defaults in R to make a good choice for you, because it might not be the right way to do it. So I think that's just about everything that I wanted to say about how to actually do linear regression in R.